Yeah, so your test is a week from today.
Yeah, first chapter 6 through 6.5.
Well, might be more than 6.5. Let me see.
Well, it's like the 6.8 or 9. 6 on the syllabus.
Yeah, we will go, no, it'll be through 6, 8, but not including 6, 7. Okay? We're doing 6, 6 today. So this is kind of one of the main points of why we study logs and exponentials. Not the main point, but is to be able to solve logarithmic and exponential equations. So everything we've done up to this point has led us to be able to look at problems like this, all right? So remember last class we did the properties of logs? Right, we had properties of logs last class. Expanding and condensing. That sheet I gave you, does everyone have that handy? Yes? Okay. So let's start off looking at a couple of things that we need to remember. Remember, since both exponential and log functions are one-to-one. Remember, they were inverses of each other, right? And in order for a function to have an inverse, it had to be one-to-one. So because of that, we have the following properties. First, if I give you log base a of x, and I tell you that that's equal to log base a of y, what does that mean? That means that whatever's inside this log must be equal to what's inside this log. Now that might seem obvious to you, all right? That might seem obvious that the insides of these functions must be the same if these two are equal. But see, it doesn't always work that way. Let me show you a quick example. I'll do it on the side off camera. What if I tell you that f of x equals 4 and f of y equals 4? I'm not going to tell you what the function is. Does that mean that x is equal to y?
Not always.
Not always. So let me tell you what this example was. The function f of x is x squared. So I could have plugged in 2 and gotten 4, or negative 2 and gotten 4, right? And 2 and negative 2 aren't the same. But that's because x squared looks like a parabola and is not a one-to-one function, right? Fails the horizontal line test. But because of the fact that it is one-to-one, that if you have the log equal on both sides, then the thing that's in the log must be equal. What do we call the thing inside the log? Called it something last time. Can I remember? Argument. It's the argument of the function. So that works for logs, but it also works for exponentials. So if I say a to the x equals a to the y, that means that the x must equal the y. Have y'all ever seen this symbol before? It's an implication symbol. Y'all ever seen that? Therefore? Yeah. Let me show you that symbol a little bit because I want you to, some of you are doing more math, so I want you to see what this symbol means because it's actually a very important mathematical symbol. What if I write this down? If you're a Texas citizen, then you're a U.S. citizen. Is that, you agree? Yes? Another way of writing that would be to write Texas citizen implies U.S. citizen. So if you're from Texas legally, then you are legally a U.S. citizen, right? That's what that means. Understand? Now, this means that if this is true, then this is true, right? But watch what I'm about to do. What does that mean? It implies both ways. That means if x equals y, then this is also true. So this implication goes both ways. So whenever we use that in mathematics, we say this symbol. We say if and only if. And we like to write IFF for if and only if. So just double implication. Is this a double implication? Is this an if and only if statement up here? No. No? Doesn't work the other way? Try it the other way. If you're a U.S. citizen, does that mean that you're from Texas? No. So that implication does not work both ways. So this is not an if and only if statement. Understand? So I just want to give you a little background on that symbol. All right, let's get down to today's business. And I apologize if I sound terrible up here. I actually feel okay, but I sound horrible. All right, so let's solve. We're going to start with log equations first. And I'll put a reminder up here of how we attack a lot of these, but let me go through one first, all right? So how about 2 log base 5 of x, here's an example, equals log base 5 of 9. So can I use the property I just showed you? Can I just say right now, okay, log base 5x, log base 5, 9, that means x equals 9?
No,
No, why not?
because of the 2.
The 2, right? The 2 out front is messing things up. So what can I do?
Put it on that.
Put it on the x, right? We can use the property of exponents from logarithms from last class. This is actually property, where the heck is it?
What is it, L3?
Property, yeah, it's L3, right? It says log base a of x to the y comes out front, or if the y's out front, we can push it back up as an exponent. So I'm going to push this up as an exponent. Log base 5x squared equals log base 5 of 9. Which means? Which means x squared equals 9. Now we can use the property I've just put up on the board. Right? Because the inside, the argument of this log, must be equivalent to the argument of that log. And how do you solve that? Square root both sides. And when you take the square root, you always have to do plus or minus root 9, which is just plus or minus 3, right? Okay. But we have to check our answers. This is the drawback with log equations. You what? You can't have, you have to be careful with the way we say that. It is okay sometimes to have an answer that's negative. The important thing is that when we plug that answer into the argument, it's not negative. All right? That's the important thing. A lot of people, they look at these answers and they just throw away the negative one. You have to check them. All right? So you'll see that when we do some more examples that it is possible to have a negative answer. All right, so let's check our answers, because one of these doesn't work. So to check, what I do is I plug my answers into the original equation, the original one, before we pop that 2 up here. All right? So 2 log base 5, let's do the 3 first, equals log base 5 of 9. Now we don't need to check this in terms of like getting our calculators out. We don't. We just need to make sure that everything works okay. I can never plug a negative into a log, right? When I plug the 3 in there, that's not a negative. So I can take log base 5 of 3, I could do that on my calculator, I can multiply by 2, and it should match this side. So I'm going to say that this is okay. I'm just looking for problems with the domain. That's all I'm looking for. So here I was checking 3, right? I was checking 3. Now let's check the other answer, which was negative 3. To check negative 3, I put 2 log base 5 of negative 3 equals log base 5 of 9. Does this work? I'm hearing.
Because you can do, yeah, you can do that, or if you bring the 2 over, then it.
All right, this is a very important juncture of this and just in general when you're looking at checking solutions. When you're going to check an answer, you must check it in the original format, okay? Before you did any properties. So bringing that 2 up and see if it works before you do anything, algebraically, before you pop the 2. And if I try this, I cannot do that, all right? You cannot plug a negative into a log. This would be undefined. So the negative 3 doesn't work. I'm going to give you another example to help you see why you have to do. You can't do anything with. You have to check it before that 2 would go in.
So if it
But
was
even
already
if the 2 is already there, like, it won't multiply.
You have to check it before you do any algebra. Okay, let me give you another example next to this. Let me just say this. Undefined. Right? This is undefined right here. Plugging a negative into a natural log, or into a log. So
Because with your base you can't get it.
it's impossible to ever raise a number to any power, right? This means 5 to what power is negative 3? That's never going to happen. So this is impossible. So what is the solution to this problem? 3. Okay, 3 is the only answer. Now let me try and reiterate why it is, again, that you cannot simplify algebraically. Okay, look at this equation right here. Give me the solutions to that equation. All real numbers? What about 0?
Except for 0.
Why not 0? Because if I try 0, it's just 1. I mean, sorry, 0 over 0, right? Which is undefined. But if you were to come in here algebraically first to try and simplify, you would have said, but x over x is 1, wouldn't you? And then you'd say 1 is 1. And so now you'd say, well, look, I can use anything. No matter what I let x be, this is always true, isn't it? So you must always look at domain issues prior to any algebraic simplification. So when you cancel these x's, which we do all the time, we cancel things, we always have a little asterisk next to it. Okay, when I cancel this, that I'm telling you, without telling you, that x can't be 0. I can cancel these as long as x isn't 0. I can bring the 2 up as long as this was something I could evaluate. But I couldn't evaluate that, so I can't bring the 2 up. Does that make a little more sense?
Yeah.
Okay.
Well, I was wondering if even if the 2 is out there, but you can't multiply anything that's a negative because it's undefined.
If you bring this up here and square it, I agree with you, it's no longer negative. But the thing is, you're not allowed to bring it up until you can say for sure that that's something that you can do.
Okay.
All right, it's subtle but important. All right, let's look at another one. All right, log base 5 of x plus 6. I'm just doing the examples in the book because I figured if I do these, it should be enough to help you with the homework. They follow along pretty closely to the layout of the homework. So. All right, does anyone see a difference between this one and the prior problem?
There's no log on the other side.
The last one we had logs on both sides, right? Well, I could move one of the logs over, couldn't I? And then I'd have logs on both sides. So I agree, but there's something else.
You can combine with the property.
You could combine these into one log, right?
Or the one itself is also log base 5 of 5?
That's pretty clever. It'd be log base 5 of 5. Right? Log base 5 of 5 is 1? Okay, we won't need that though. Just bear, all I want you to see right now though is the difference between this one and the one before. Okay, last one we had 2 logs, right? Did we have a number by itself without a log in the last problem? No. This is something new, right? We have a number by itself. So let's see how we would attack this. I did hear the correct first step, which would be to combine these into a single log, and that would be using property L1. Right? 2 logs with addition between them become a single log, and this is what we spent a lot of class time, right, on Wednesday doing. So don't I multiply these 2 pieces together? So watch the way I write this. I'm going to go x plus 6, x plus 2. I still need to multiply those together, don't I? But equals 1. I put a big set of parentheses just to kind of reiterate that this is the argument of that log function. Now, even though I do like the idea that you could convert this over to log base 5 of 5, even though I like that, I'm going to go back to the loop. Do you remember the loop? I said that I like to use the loop for logs. That loop is what I'm going to use to solve this equation. So do you remember how the loop worked? Take the base here. You say that, what? Raised to this power must equal everything in there. So what I'm doing is I'm converting now from a log equation over to an exponential equation. Right? This is how we converted back and forth. All right, so let's convert this. This becomes, what, 5 to the first power must be equal to x squared, or sorry, x plus 6 times x plus 2. Now what? You're going to have to multiply that out. Because this is what type of equation now? It's a quadratic equation. Why can't I do this? Because I see students do this all the time. They're like, oh, okay, it's already factored. I just set that equal to 5 and then set the other factor equal to 5 and just solve each one.
Because it's the whole thing has to equal 5.
That's right. These 2 multiplied together have to equal 5. Now, why do we do it when it's 0, though? When it's 0, don't we set each one equal to 0? So why don't we do it when it's 5?
Because 0 is already, because
I'm just asking you to think about this, right?
it's 0.
Because it's 0, that is right. Because look at this. If I tell you A times B equals 0, the only way that can ever happen is if A is 0 or B is 0. Do you agree? I don't care. You can come up with any numbers you want. There's no way you can get 0 unless one of them is 0. Right? But if I tell you that 2 things multiply to be 5, does that mean that one of them has to be 5? No way. I can give you an example. 25 times 1/5. That multiplies to be 5. Neither one of them are 5. Right? Yeah, but I mean, I could go 3/4 times, let's see, 20/3. There we go. Right? I mean, I can make it crazy. I could put other things in there that would not be, there wouldn't be a 5 in there, right? 20 goes into 5, yeah. So anyways, the point is that when we are setting something equal to 0, it's called the 0 factor property. And the big mistake I see on students, they'll get all this right and then they set both these factors to 5. That's a huge mistake. I see it in my Cal 1 classes and I'm just like, whoa, that's a huge, huge mistake. So I'm only mentioning this because this is like a prerequisite topic for the class, but it's so important that you understand that you can't just set these equal to 5. So that's why I have to multiply them out. I have to multiply this side out. Excuse me. X squared plus 8x plus 12. So I expanded this out, FOILed out, and did all my combining together. Now bring everything to one side, because this is a quadratic equation. So I'll subtract 5 on both sides. And you're going to have a quadratic equation now, right? And your hope is that you can factor it. If it doesn't factor, what can you use? Quadratic formula, right? But this one factors. Factors to be plus 7 plus 1, right? Now you can set each of those factors equal to 0. Do you see the difference? This problem is not as simple as setting each one to 5. It actually turns out to be this, which is setting each one of these to 0. So what are my two potential answers here? -7, -1. Question mark, though. See, because when you're sitting there initially looking at that, you're like, they're both negative, right? So you don't use them? Well, you have to check them into the original problem. We're going to see that one of them does work. All right? So here we go, checking. Do you understand what I mean by don't just throw them out because they're both negative?
Yes.
Okay. So let's check -7 into the original problem, which was log base 5 x plus 6 plus log base 5 x plus 2 equals 1. All right, we try and plug -7 in here, right? It turns into log base 5, -7 plus 6, -1. I'm done now, right? I mean, I don't need to continue, but I'll write out. I can't do this, right? You try and type that into your calculator, you're going to get an error. This is -5 here, equals 1. No way. Undefined, right? So that means I'm going to scratch -1 or -7 from my answers. I've got to do the same thing now. I'm going to check -1. Log base 5. Let me go ahead and just plug -1 in now. What would I get there for that first one? 5 plus log base 5 of 1, and then does that equal 1? I don't even need to check that it equals 1. I just need to make sure these can be evaluated, which they can, because they're both positive, right, inside the arguments, so I'm good to go. But it does work. What's log 1 of anything? Like, this is always 0, right? And then 5 to what power is 5? 1. So this is 1 plus 0 equals 1. That checks. So we do actually have confirmation pretty easily that that was a solution. But we were trusting our algebra that, look, these are potential solutions. All right? We good? All right, let's look at another one. Ooh. Natural log x equals natural log of x plus 6 minus natural log of x minus 4. Now this is different from the last problem because now we have 3 logs, don't we? And so what do you think? What do you want to do? You want to combine the ones on the right side? Okay, so I can put these together using L2, yeah. L2, the property of logs, formula 2. The subtraction becomes a single log with division, right? And what goes in that division? X plus 6 on top over x minus 4 on the bottom. Now what? You can do what? X equals what? Oh, you can take the argument of this one and just set it equal to the argument of this one? Yeah, do you all agree? Look, this is like natural log x equals natural log y, isn't it? You have logs on both sides, so you can do that. In the previous problem, the reason I used the loop is because one of the sides was 1 and the other side was a log, so I can't use this property unless the log appears on both sides. Understand? So I just set x equal to the other side, x equal to this. So this becomes x equals x plus 6 over x minus 4. The last problem we did, it turned out to be a quadratic equation, didn't it? This problem is turning out to be a rational equation, right? And we studied this. This is one of the things that actually remember you had to do that packet in the beginning of class, like the things that you were supposed to know how to do. This is one of them, right? So how do you solve a rational equation? Find a common denominator, which in this case would be what? X minus 4, and then multiply both sides by that common denominator. So that's what I'm going to do. I'm going to come in here with my LCD, which is x minus 4, and I'll multiply both sides by that x minus 4. That look familiar? That has the effect on the right side of killing off the x minus 4 in the denominator. On the left side, I have x minus 4 times x, which I'll distribute that on the next line. This becomes x squared minus 4x equals x plus 6. And what type of equation do we have now? Quadratic again. So we started with the log equation, used the properties of logs to get it to a rational equation. The rational equation turned into a quadratic equation, and now the quadratic equation we will hopefully get 2 solutions for. So everything to one side, right? X squared minus 5x minus 6 equals 0. Is that factor?
Yes.
Been getting lucky, haven't we? I'm going to leave the original problem up here because I'm going to be using it to check in a minute. So this is x minus 6, x plus 1. Set to 0, and we get 2 solutions potentially, right? Does anybody know what it's called when you have a list of potential answers where some of them could not work? Does anyone know what we call the ones that don't work? Very good. Extraneous solutions. Again, this is just language. As you move on to doing more math, you want to start to, it's not just about can you do the math, like it's just the terminology of things. So whenever you're doing logarithmic equations, there's a potential for extraneous solutions. So you must always check your answers. We'll see that when we switch over to exponential equations, which is the next topic today, that the checking doesn't have to necessarily take place, which is good. But here we have potential for extraneous solutions, so we check these. So can I check them just visually real quick? Plug 6 in. Can I do natural log 6?
Yes.
6 plus 6, 12. Okay, 6 minus 4, 2. I should be okay, right? All right, negative 1. No, can't do that. All right? So my only answer is 6. Let me give you one more of these, and then we'll switch over to the exponential. Keep that. Did someone say wait? No?
What was, you said extraneous?
Extraneous solutions. Oh gosh. E-X-T-R-A-N, wait. E-O-U-S. I don't know if there's an I. Yeah. Google it, okay?
What does it mean now?
It's extraneous solutions or solutions that you actually get when you're doing your algebra that don't work.
Okay.
All right? That have to be checked to verify that they don't work. So no I in there?
No I.
Okay. All right, how about this one? This is a type of problem that I give on a test, and then people like freak out. I'm not sure. Just like that. And they get all mad because, like, you didn't do anything like that in class. And I'm like,
It's 7.
all right, you ready? So we do have a number by itself again. And we have two logs with addition that we could put together. So let's go ahead and put those together. That's L1. Right, I'm using L1 here. It'll be, I have to multiply those two together. So x times x plus 2. And then equals 3. And this is where the wheels start to come off.
Wait, so in the natural log symbol, that's an LN, right?
It's an L, yes.
Okay. Use that one.
No, it's because it's because that matches your calculator and stuff. No book or calculator I've ever seen uses a capital L.
Mine does.
On your calculator? Oh, but yours is all caps on the T89?
84.
84? Yeah, it's all caps. Like if you look in the book, I mean, if you look in most text, it's a lowercase L.
But here it's lowercase n.
Yeah.
So I think you should change it.
Yeah.
Consistency.
Well, you know what? I'm going with what is generally accepted. Okay, that's the general. Go look in, 90% of the books probably are going to. I know you are, but you're bringing up a good point. Because I have students that think that this is IN, and it's not. It's LN. I have, like on internet classes, I'll have students come in for help, and they're like, and on this in function, I'm like, in? What are you talking about? The in function. Okay.
I mean, all your stuff is capitalized.
You're right. I know. Okay. All right, well, here we go. What do we do? You want to multiply the inside out? Okay, I'll do that.
Now we need to clear the
Can we do the loop thing?
We can do a loop thing. But what are you going to loop it with? Okay, that's the part you have to remember. The natural log, there really is a base down here. We don't write it, right? And that's where people are like, well, what do I do? So what a lot of people do is the next line, this is a huge mistake on exams that I see, they'll write x squared plus 2x equals 3. And they don't do a loop, they just get rid of the log. And then this is actually workable and they're all happy about it, but it's completely wrong. So what we need to do instead is we need to realize that there's really an e down here, right? There really is an e, and then create our loop from that. With me? Okay, so now the next thing is to rewrite that in exponential form. E to the 3 equals x squared plus 2x. And then, what do? Use a calculator, that's right. You're going to figure out what e cubed is. And you're going to have to approximate it. 20.085. Let's go 20.1. How about that? Good enough?
Yes.
All right. So this is approximately 20.1 is approximately equal to x squared plus 2x. And that's a quadratic equation. So we move everything to one side again. And you're not going to be able to factor this. Yeah, I don't know why I did that. Sorry. Thank you. So I'm going to stop writing approximately because the rest of the way we know it's going to be an approximate answer, right? I've rounded, and so I know my answer is going to be off a little bit, but should be just a little. All right, so here, you look at that. Since you can't factor it, you have to use quadratic formula. So this is what I say people get caught on a test. Look, I would expect everyone knows that natural log, the base is e, so that you do the loop. This is a quadratic, right? And I expect everyone here could solve a quadratic, whether it be factoring or quadratic formula or whatever it is, right? So you just have to kind of look at math that way from here on out. It's like anything that you've done is kind of, on the table, so to speak. You ready for quadratic formula on this? Should I identify A, B, and C for you, or are you past that? You past this? I hope you're past this, but I'll put it on here anyway. That's your A, B, and C. And then the formula is negative B plus or minus the square root B squared minus 4 times A times C all over 2 times A. So what do we have here? Negative 2 plus or minus square root. What do you get under there? You have to do like 20.1 times 4 and
404.01 is the,
inside there?
is the, oh wait,
It's negative 80.4.
Yeah.
That, oh, what, then it's a positive. So
It's a plus, yeah, right?
Yeah.
So it's 4 plus 80 point.
84.4.
All right, that's what you should get, and then add them together, 84.4.
Wait, I got 84.4 by doing 4 minus 4 times 4 times.
Can't do that. Order of operations, this is multiplication. You must do multiplication first.
So you get a negative 20.1, and then you times that by 4, you get 80.
Yeah.
Or by
So look,
negative
here's the deal. Look, I'll be completely honest with you. You have to go back and review quadratic formula, okay? To get through, to say you passed 1414, you cannot be getting hung up on quadratic formula. I mean, that's part of the deal. You've got to be able to do this the right way, right? I mean, you know what I'm saying? Okay. But, okay, but I'm asking you to go back to, you know, the past and be able to, you know, just go through it again. Yeah, there are certain things you have to pay attention to, but in no way do I feel like we need to review it as a class, right? Let's take the square root on our calculator. What's square root of 84.4?
9.19.
Okay. Over 2. Wait, what was it? 9? Yeah. 9. And then now you put these two answers together. So how do we do this? Negative 2 plus that first, then divide by 2, right? Then negative 2 minus that, divide by 2. So we have two different answers that are coming from this. From that, there are two different answers. That's an equal sign. We have negative 2 plus 9.19 over 2, negative 2 minus 9.19.
The negative 2 is 3.595.
Which one, this one? You added,
Yeah, you added that one.
is 3 point what?
3.595.
Okay, good enough. And then this one, yeah, negative 5.59, something or. Those are our two potential answers. Then you have to check them. I think the negative is the one that's not going to work, right? I mean, you have to go back and look at the original equation, and it won't work. It's about 3.59. All right? All right, so now let's look at, we're going to switch gears here. We're going to go to exponential equations.
Maybe it's kind of always
Hey, remember how I put a parentheses on the log equations, and I said I'd tell you what to put in there? Just remember the loop. We didn't use the loop every time, right? But just remember, like, that is one of the main keys in there. So where I put that parentheses on that last one, just put in there, you know, remember the loop for those types of problems. Remember the loop. Remember when I started logarithmic, do you have, keep going.
In the way beginning?
Yeah, in that parenthesis I left up there, I said I'm going to come back and tell you what to put up here.
Oh.
Just remember the loop. All right, exponential equations. We should be somewhat familiar with this because we did start tackling this idea before. So we had run into a problem like this where we couldn't do it by hand. So we looked at it, we said, okay, 2 to what power is 5? Well, we don't know what that is, right? And we would say something like, oh, we can rewrite this from exponential form into log form, right? Now, don't write this down, but let me just remind you, this is the way we did it before. We said, this is the same as log base, what? 2, and then 5 equals x. And then we got on our calculator, and we did the change of base formula over here, and we got an answer. We went to our calculators. That's how we did it prior to today. Yes? I'm going to do it different today. Because this way is a little bit too tedious for where we're headed. These are going to get more complicated, all right? So here's what I'm going to do. I mean, you could do it that way, but just see if you like this. Do you remember, let's everyone look at property 3, L3? Yeah, L3. It said if you have log base a of x to the y, we pull the y out front, right? And that also worked for natural log, didn't it? So if I had natural log of x to the y, this was y natural log x, right? This property right here can be seen as anytime you have natural log of something to a power, you can always drop the power out, right? So what I'm going to do here is I'm going to use that property against this problem. I'm going to come in and do natural log on both sides of this equation. So I'm going to write this down. You just tell me if this is true or not.
Yes.
It's not true. No. It's true. All right, so what I'm using is a couple of things here. This is actually the one-to-one property that I started class with. Didn't we say that if natural log of x equals natural log of y, that x has to be equal to y?
Yes.
Yes? And it was an if and only if statement, so if these two are true, then this is true also. But mathematically what we're doing is we are taking the natural log of both sides of the equation. You know how you've done things before, like you've squared both sides of the equation? Right? The way we would say this is that we're taking natural log of both sides. You do not say I'm multiplying both sides by natural log. That's incorrect, because natural log is not a number. Natural log is a function. You can't multiply both sides by a function. You can compose both sides with the function. That kind of makes sense? All right, so why did I do that? Why did I come in here with the natural log? We're trying to solve for x, aren't we? And that x was trapped up here, wasn't it? And we wanted to pop that x out and get it down. And putting a natural log out here in front is going to allow me to use this property to take that x and drop it out to the front. All right? When we do that, we'll have x times natural log 2 equals natural log 5. And so now since this is multiplication and we're trying to get x by itself, we divide both sides by natural log of 2. Right? You want to get this out of here? Yeah. Divide both sides by natural log of 2. Isn't that exactly the same computation we would have done had we done the change of base formula? Yes. It's the same thing, isn't it? So go ahead and get your calculator out and let's get an answer here. It's going to be a decimal. $2.32. That looks good. The way you type this into your calculator is critical, which is why I've been wanting you to bring your calculator so you can get acquainted with your calculator, right? You don't want next Monday to be the first time you're borrowing your cousin's calculator and you don't know how to work it. Because if you're like during the test, like, I don't know how to use this, I'll be like, you've had 2-3 weeks to figure out how to do logs on your calculator. I'm not not going to assist you. And then if you don't bring a calculator for the test, you can't borrow mine and you can't borrow your classmates, all right? Unless you arrange that before you walk in, all right? So not like right, oh, I forgot, does anyone have a calculator? Like, y'all need to take it outside, do it out there. People have calculators. The reason why is this, because let's say there's 3 people who don't have a calculator and I only have 1. Like, I'm not going to loan it to one person and be like, well, the rest of you are screwed. Or you know what I'm saying? It's just not fair. Bring your damn calculator. It's pretty simple, okay? All right. What do you think? If you want to pop the x out, you bring in the natural log on both sides. Now, why did I use natural log? Why didn't I use, like, I don't know, log base 4 or log base 2? Why not use log base 2? Because that's already a 2 base, right?
Because then your bases aren't the same, you can't do the same thing, right?
Let's see what would happen, okay? Because people, I've heard people get upset with me that I'm not using log base 2. They're like, my teacher showed me to use log base 2. Here, what if I did log base 2 of 2 to the x equals log base 2 of 5? What if I did that? What's the advantage of doing it this way? Just tell me what would be nice on this side. What is this? Look at property. This is property, where is it? Property 4. Look at L4. What's log base a of a to the x? Just x, right? Wouldn't it be? So the left side is already x. So you might argue that's a lot easier. But what's the right side? Change base. You have to do the change of base formula, don't you? Which would be natural log 5 over natural log of 2, which is the same as this. So I mean, there's not much difference in this. The advantage, I think, of coming in with natural log is because your calculator has natural log, so let's just use natural log, right? Okay. Now, I'm going to step out for a second because I'm all congested and I don't want to sit in here and like blow my nose and sound all disgusting. So I'm going to step out and let you try this one. If I wasn't recording, I wouldn't care. I'd let it rip. All right. multiply 8 and 3 together?
Why would you do that?
Well, because some people do. Can you multiply 8 and 3 together? Could you make the 8 times 3 24? Think about this for a second. If I have 8 times 3 squared, is that equal to 24 squared? What's 3 squared? 9? 9 times 8? 72? 24? No way, right? 24 squared is huge. So order of operations. Don't you always have to do exponents before you do multiplication? You can't put these two together unless you raise it to the x, and you don't know what x is. So you're not allowed to hit that 3 with that 8. So divide 8 on both sides first. Okay, good. So divide 8 on both sides. You get 5/8, right? Whatever that is. I'm not even going to get on my calculator for that.
Yes.
Now, release the 8, or the x. How are you going to release the x from there? Natural log, both sides, right? So natural log 3 to the x equals, now don't forget natural log of 5/8 over here. Right? The x pops out like this. You get x times natural log 3 equals natural log of 5/8. Now divide by natural log of 3. So this will be a good exercise on your calculator, whether or not you can do this correctly. You have to take 5/8 and take the natural log of it. Then divide that by the natural log of 3. Now, a lot of you have calculators that you can type it all in at one time, and that's great. Just be careful with your parentheses. Whoa. I have a 6-year-old, right? And she's going through this thing right now where she wants me to take pictures of every little living creature she finds. Daddy, there's a grasshopper. Take a picture. You know, eating it. Okay, I'm letting you do this on your calculator while I check.
Because I got the vice principal class, she's only 6.
Uh-oh. So x is equal to, let me tell you what I'm getting for natural log of 5/8. Getting negative 0.47, and then a bunch of zeros after that, like 3 zeros. And on the bottom, natural log of 3, I'm getting like 1. What? You did? Okay, let me double check.
Natural log of 3.
Are you using your phone calculator?
Yes? Find them.
Dang, shots fired.
No, it's right.
I got,
Natural log of 5/8.
the top I got, but the bottom,
I got 0.05.
oh wait, you know what, I had already did, hold on, because I had already solved it. Okay, yeah, that's right, and then I got,
And then you have to divide that.
or negative 0.43.
We're all
Wait, wait,
Equals negative 0.4278. Yes, no, I was trying to show for people who are trying to do the top and bottom separately, you know, what you should be getting for the top and bottom. Because some people, like on some of these calculators, you have to do it like, you know, one at a time. So,
I have a question.
yes.
If I pushed the log button instead of natural log, should I have gotten the same answer? And I did.
What did you do? You used log of 5/8 over log of 3? Yes, it would work. It turns out that you could have used any log. Remember I said you could have come in with log 2 on both sides, or why use natural log? Because most people have the natural log key. Does that one have a natural log key?
It does, I just.
Okay, yeah. Yep, it does work. Everything seems nice right now, doesn't it?
always does.
All right, next example. 5 to the x minus 2. Bye, have a good day. 3 to the 3x plus 2. I was thinking about Lily, what's her name, Lily? Lily? Full Metal Jacket came on last night. They're going through that training. I was thinking about her. Way I've learned not to talk about people when they're not here on camera. They get real sensitive.
Yeah. Maybe Paul's probably training them.
It was.
All right.
We got the class pretty early that day.
Yeah,
You know you missed those.
I said I did.
I felt really bad not coming to class that day. It's the first day I came to class.
All right, what do you see here?
We still have that guy.
Well, we need the same basis, don't we, so that we can
What's different about this problem?
different bases?
You do have different bases. You have x's in both sides, right?
Yes.
So when it comes to dropping x's out, you've got to do it on both sides. But that's okay, right? Because what we've been doing is taking the natural log on both sides anyway, and we've been dropping the exponents down. So let's still come in here with natural log 5 of x minus 2 equals natural log of 3 to the 3x plus 2. And then be real careful here. You're going to drop the entire exponent out front. Drop the entire exponent out front of this one. So when you write this, you have to write x minus 2 in parentheses times natural log 5 equals, in parentheses, 3x plus 2 times natural log 3. You see how important the parentheses are there? I mean, this is something, right? There's a number. That whole number is being multiplied times this. That whole number, whatever it is being multiplied times that. If you write it like this, then that only means the natural log and the 2 are being multiplied. That's incorrect. All right, so we had to solve for x.
I mean, I guess we could divide by natural log.
You could divide to get this, but then you're still going to have x's over here, right? So what we're going to try and do is get all of our x's on one side, everything that's not an x to the other side, all right? But to do that, we have to free the x's from the parentheses, which means we have to distribute the natural log of 5 through. And we have to distribute the natural log of 3 through. It's going to look weird. We've never really worked with anything like this before. So let's just see how it works, all right? When the natural log of 5 comes through, I'm going to write it like this. How about natural log of 5 times x? Because that's what that is, right? Natural log of 5 times x. And then minus, I'm going to write this one 2 natural log 5. You know what? I think I'm going to put this x in front of the natural log 5 instead. All right. Chill out. It's all right. That's why you write in pencil.
I don't make mistakes.
Any questions on that distribution? The order didn't matter, right? X times this or this times x. There's actually a reason why I didn't like it the other way. If I write this, you might think the 5x is actually together inside the log. But if I put the x in front, there's no confusion, right? On the right side, 3x times natural log 3 plus 2 natural log 3. Now I've freed the x's from the parentheses, right? So let's get all the x stuff on one side. So this one right here, this one right here, we're going to move those, let's say, to the left side. Everything that does not have an x, let's move it to the right side. That sound like fun? All right, so here we go. I have x natural log 5, bringing this one over, minus 3x